Good day, academians, or welcome to Maths and Science Academy. This is VPM scenarios. So I'm going to be going through scenario number 1, 2, until we continue to wherever. Now, guys, I always want you to do this. Whether you asked or not, always, let me not say always, because sometimes they choose the direction for you. So let's say choose first direction of motion as positive, of motion as positive. Who's going to do that? You in an exam, right? You are going to do that in an exam unless stated otherwise. Always choose the first motion, direction of motion as positive. So in this case, let's go to scenario number 1. What does scenario number 1 say? Scenario number 1 says that a ball is thrown and caught at the same height. What does it mean? It is caught at the same height. It means that you're going to be here. This is the ground. You're going to throw the ball. Then you're going to catch it also at the same level where you throw it. Right? Now, the properties of that movement, if you see, it is some sort of a cave. Right? Now, if you see here, V initial is going to be greater than 0. Why is it greater than 0? Because the ball was thrown. The ball has V initial being equal to 0 only if it was released. If there was no force exerted to give the ball motion, then we can say that that object is not a projectile, but it was released, right? It's in free fall, right? So now what you're going to do is you see something over here that is very interesting, right? Because the ball, you're going to throw it, then it's going to come at a certain point and then it changes direction. At the point where it changes direction, that peak, right, in a function sort of perspective, we call it the maximum. We have not done that in terms of mathematics, but if you know it, you know it. It is the maximum point of the motion, right? It is the highest the ball could ever go. Now, at the maximum point, or at the maximum height, it is where the ball changes direction from going up to going down, right? Now, what is special about that certain point is that there, the ball's velocity is equal to the Vmax is equal to 0. So this over here happens always at maximum height. Always at maximum height. By maximum height, as I said, it is the highest the ball could ever go. So meaning the highest, it will change direction because it is its maximum point. It is the barrier, right? What is going to happen? The ball is going to change direction. Now, what you must take note over here, right, is you must take note that now, if the ball's velocity is 0 over here, right, but if it goes all the way back to where it was and it's caught at that same height to where it was thrown, the velocity final, right? The velocity final is going to be the same as the velocity initial, but in the opposite direction. Because they are caught at the same point, they are thrown and caught at the same point or same height, their velocities are going to be equal, but in the opposite direction. So V initial is going to be the negative part, V final, which is C, is going to be the negative part of VI, because as we see that VI is going up. Now for direction, I want you to take note. For direction, which one am I going to take as positive? I'm going to take up as positive. Why? Because that is the first direction of motion, right? It means that my gravitational acceleration is going to be negative. Why? Because the gravitational acceleration always acts downwards, right? So if I chose positive to be the upwards part, it means that downwards motion, it is negative. Since this one is always downwards, it means it's going in the opposite direction as positive. It is going downwards to the negative part, so that's why it is negative 9,8. Now, you don't say because the ball goes here, then the acceleration is negative. Then when it goes here, the ball is going down and the acceleration is going down. Now the acceleration is positive. No, the acceleration, that's the system only chooses the direction once. That's why I'll always advise you in one question, choose the direction once. Yeah, always choose the direction once, and then you're going to continue in terms of that question. And when you finish it, you can then choose another direction that you're comfortable with in the other question. In this question, in one question, you always choose one direction, so you know that this system only acts when up is positive and down is positive. Don't tweak your things and say, oh, because the ball is going down and acceleration is always acting down, it means that the acceleration is positive. No, if I choose up as positive, it means that my acceleration is negative, because the acceleration always acts downwards, and what is down? Down is negative. It means that acceleration is going to be negative throughout the equation, not because the ball is going down and the other one is going to be going down. No, it doesn't work like that, right? So we must always remember that if the balls are thrown and caught at the same height, right, and caught at the same height, their V initial, the V initial is going to be greater than 0, of course, because it is thrown. But because the velocity final is going to be the same as the V initial, even though we don't know it, if we had, let's say if you had V initial as 15, V final would be negative 15. It is the same, but we're in the opposite direction, meaning that this is V initial meters per second way up, because it's what? It is positive. This is V initial is going to be 15 meters per second way down, because it is what? It is negative. Of course, in an exam you wouldn't leave it negative, but we're trying to explain over here, right? Now, what you must also remember is that the time it takes, let's say for T1, if we go from here to here, right, and the time to go from here to there is T2, we can conclude that since the ball has the same direction, meaning that it goes from 15 to 0, and also the other one goes from 0 to 15. It's just the same thing. 0 to 15, 15 to 0 is still the same thing, right? It means that T1 is equal to T2. It means that if you calculated T1, if you wanted to find the whole time it takes for the ball to reach point C, you were going to say that maybe calculate T2, right, T1 rather, and multiply it by 2, because it will give you the ball from here and again to here, right? So you must be careful of that. These scenarios, they show up in exams. When it shows up, you'll be able to relate it and say, oh, it's the same as that scenario that we did in class, right? Now, we're going to remember, there's nothing that I'm forgetting. I covered the direction, I covered the final velocity, I covered the displacement. Okay. The acceleration, okay, everything is fine. I just want us to draw, because I know this is a struggle for a lot of people, right? Now, I want you to remember this. Take notes of this. In this, let's start with this one. In the position, this is what we call the position time graph. Now, what is displacement say? Let's just explain displacement, because I know a lot of people are going to be very lost. Displacement. Some people may say displacement like this, right? We can see that it is the change. It is the change in position of the object. Now, let's say, for example, you're at point A. Then you go to point B, but the route that you take is this one. What is the displacement? You're going to calculate your displacement. It is a straight line from where you started to where you are currently. But if they say, what is the distance? The distance is the whole of these curved lines over here. All of these curved lines. That is the distance that took you. But displacement is a straight line drawing from where you started to where you are at a certain point. So always remember that. I think that was very helpful. I know, right? But now, we must always remember this. Right? In this particular graph, right? Right now I'm doing graphs. For this motion, I'm going to show you how to do it. For this motion, can we clean this, guys? Let me try and clean this, because It is very untidy at this point. Let me clean this. Yes, it can be cleaned. Yes, it can be cleaned. Yes, it can be cleaned. Okay, okay. Thank you for that. Yes, 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 yes. I'll draw a line again. It's fine. It's fine. And then we can remove this. Remove this so it can be clean. Clean, 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 clean. Yes, yes. That's more like it. That's more like it, right? Now, what I wanted to do, always remember that this here is what we call a position time graph. Position time graph, because I just explained displacement and then there's a change in position. So this is a displacement versus time graph, and we know that displacement is just a change in position of an object, right? Now, I want you to say this with me. The position time graph always take the motion of the object. The position time graph always take the motion of the object. Let's do it like this, right? If it is a Z, you're going to draw a Z over there. Okay, I'm just joking, but it's fine. This let me confuse you because you're going to remember that part only. And my teacher always said that, but it's fine. Let's continue. Now, what you must remember, right? If we take the ground as a 0 reference point, they will always say that it means this is your 0. So you're going to start over there. That's where you start. That's your 0 point, right? Now, what you're going to do is they're going to say that the ball is going to displace, right? Now, displacement, guys, displacement works like this. Let me explain it very quickly because it confuses a lot of people. Let's say you are here and you throw a ball over here. And then you choose, let's say up is positive, right? Up is positive, meaning down is going to be negative. Down is going to be negative. The ball starts at a higher point and it ends up lower. So the displacement is negative because why? Because we chose the downwards as negative and the ball ends up down than where it started. So down, we chose it at what? As negative. But in the case where you have an object over there and you throw the object upwards, right? You throw the object upward and it's here, right? What you're going to do over here, you see that the ball starts lower and ends up higher than where it started, so it ends up than where it started, and we chose up as what? As positive. It means that the displacement over here is positive displacement, and if we did for that scenario, we could have said negative displacement. Now, also, if you were choosing the directions as positive, whatever, let's see. Let's do the directions. Let's see now for directions you choose up as down is positive, up is negative. What you're going to do, still do the same thing, right? Now here the ball starts lower and it ends up higher. It ends up than where it started. What did we choose as up? We chose it as negative, so this is going to be negative displacement. Now here the ball ends up lower than where it started. It ends up down than where it started. What did we choose? Down is positive, so this is positive displacement. Oh my god, I'm so good at this. I'm just playing, guys, but I really try to explain everything. That's why I say we start you from the ground up. Now guys, I know now we're fine. Let's just go to the graphs. This is scenario number 1. Nothing too crazy, nothing too hectic. Now, scenario number 1, what are we going to have? Scenario number 1, we're going to have a motion that follows the motion of the objects. I said to you, a position time graph always take the motion of an object. Now, what is going to happen is that the graph is going to move up like this and come back to the same point. That is the position. So, if you were to label this graph, if you were enthusiastic, you wanted to label, this is the starting point, which is A. Here's the A, and then this is the maximum height, which is B. This is the ground again, which is C. What did I say about maximum height? I said to you, what is 0 at maximum height? Velocity. The velocity at the maximum height is what? 0. Do not forget that. It's always maximum height, always 0. Right? Now, the velocity time graph. This is the velocity versus time graph. I want you to say this with me. The velocity versus time graph is a straight line graph. A velocity versus time graph is a straight line graph. You'll get used to it. Now, here we're going to start with our initial velocity. We know that our velocity is not what? It is not 0. So we have to start maybe somewhere. Let's say it was maybe here. We don't know the velocity. We just know that it's greater than 0. It's positive. Right? So let's take this area as our positive area, and this downward as our negative part. Right? So if the ball is going with negative velocity, we are going to be drawing over here. We're going to be directed by who? By the direction we chose as positive or negative. Now, what is going to happen? This is the motion. Let's check the motion. This is the motion of that object. This is the motion of that object. Now, what is special? If you draw, right? The object, when it goes up, the velocity decreases. How do you see if it decreases? Because we just proved it. The object goes up, the velocity is greater than 0 over here, but it goes up, decreases until it reaches what? 0. Then when it goes again, it gains velocity, it increases, but in the opposite direction, right? The velocity is still increasing, right? But in the opposite direction, right? I said to you, a vector is a physical quantity that contributes for both magnitude and direction, right? So the magnitude of the velocity is increasing, but in the opposite direction, right? But now in this case, if you throw it up, it decreases until it reaches maximum height. At the maximum height, what is the velocity? It is 0. It means that the velocity was decreasing until it reached 0, and that's what we call the maximum height, because at the maximum height, the velocity is what? It is 0. And then after the maximum height again, it changes direction, it goes in the opposite direction, and it gains velocity. It becomes the same velocity at the same point that it was thrown at. Right? So I know I'm preaching, but this is good, guys. VPM is starting to grow on me. I'm thinking it's a very good topic. It was a good topic all along, but I'm just joking with you guys. Now, if you want to show the ball, right, we know that the velocity here, we know that everything here is 0. So the velocity here is 0. Why am I saying that? Because our velocity is the y-axis. Right? So what do I mean? Remember from mathematics, you have something like this. You have the y-axis and you have the x-axis. If you wanted to find the x-intercept, what you're going to do is make y equal to 0. Where is y equal to 0? Y is equal to 0 at the x-axis. Right? So now we're going to use that same principle over there in physical sciences and say that we are wanting to find where the velocity is 0. We're going to look at the x-axis. Why? Because the velocity is our y-axis. It is our y-axis. So if you want to find the x-intercept, we have to make y equal to 0. So we know that our y is what? It is velocity, and velocity should be negative, should be 0 on the time axis, because we just use the same method. Guys, I just explained this. I don't want to go deep into mathematics because there's some people are not writing mathematics, so it's fine, right? Now, what we're going to do is show that the graph, the gradient is decreasing up until it reaches 0, right? Now, when it reaches 0, it now increases, by the way, in the negative direction, right? Which we chose as negative, which is downward. It is increasing downwards, and we chose down as what? As negative. Then over here, it reaches that point, right? Now you must always remember this, that this over here, always label your graph, right? This here will be the starting point. This will be when it reaches maximum height, and you see that the velocity over here is 0 meters per second. Then this will be c when it touches the ground. So the velocities over here have to be the same, right? So this will be v, and this will be negative v. They're the same, just in the opposite direction. Now I want you to take note over here. The area of this graph, the area of this graph is going to give you, the area of this graph is going to give you same area of triangles, right? So these two triangles must be the same, because the time it takes from here to here is the same, and the time it takes from here to here is also the same. meaning that the speed from here to here is going to decrease the same, and also the speed from here to here is going to also increase or decrease the same. Everything is just the same, but in the opposite direction, right? But I also want you to take note, the area under the V versus time graph will give you what? Triangles. Will give you triangles. Three sided shape, right? Three sided shape. Now, those triangles, what is the area of a triangle? The area of a triangle is 1/2 breadth times perpendicular height. I want you to use this one. Do not say V versus time. No. Right? Now, if you look at these triangles, this here, let's remove this thing. Right? This here, let's say it makes a 90. This here would be your perpendicular height. Right? So that would be V. So we're going to say that A is going to be 1/2. 1/2. What is the perpendicular height? The perpendicular height is V, right? Now the breadth is going to be the time, right? The time, because it's the axis, right? It is the time. It is delta T. Now, this is how you calculate the area. But I want you to remember this. The area under this graph represents who? It represents displacement. So when you give you a graph and they say, find the area under this graph, when they say, find the displacement, you don't use the displacement formula, because they're going to say maybe without the use of a calculator. Now, not the calculator, without the use of equations of motion. So you can't use those equations that I gave you. You have to know. You have to know this, because they are going to form triangles like this, but you know that the area on this triangle will be the same as the area of this triangle over here that I'm shading, right? The areas will be the same because it's symmetry, guys. They are working together. The time it takes from there to there is the same. T2 and T1 are the same. It's the same thing, right? It's the same thing. So that's what you should look at, is that the time from here to here is the same. From here to here is the same. From here to here is the same. The velocity from here to here is the same. If it's 15, this will be negative 15, as I said. It's just the same things in the opposite direction. So the areas of the triangles will be the same. So I always want you to do this. When they ask, we'll go to past papers and you'll see what I'm talking about. The area under a velocity versus time graph, take note, the area under a velocity versus time graph is what? It is displacement. So you use it to find this way. I know a lot of teachers do not teach that, but when they say using the graph, you always have to use the graph. Do not use your own things. Now, let me not take this away, right? For those who are still taking notes, this will be very helpful, guys. I'm feeling we'll chow VPM. We'll chow VPM because we are not leaving any stone unturned. Now, what you must look at is that the gradient in any graph is just what? The change in y over change in x. Now, what is our y? Our y is v, so we can see that our change in v. What is our x? Our x is time, right? I'm picking up at the axis. The y-axis is the v, which is the velocity, and the x-axis is the time, which is delta t, right? Delta t. What is this? This is the rate of change in velocity. But what is that? That is acceleration. It means that the gradient, guys, the gradient under the velocity versus time graph is what? Is acceleration. Why say are you teaching this? Because we don't see it. You were seeing it, just that you didn't know. That's why you were getting wrong, right? Because when they say using the graph, please, guys, let's use the graph. Because in an exam, you'll go ahead and try to use the equations of motion, but you won't have 1/2 times t times v in an exam, right? So you have to know that this is the area of a triangle, as I'm given over there. Right, they always form triangles. You'll see they always form triangles, guys. So but we'll do applications, you'll understand. So the gradient under this graph is what? It is acceleration. That's what you need to know. This is special. This graph is very special. Hence, I'm trying to explain it in a very deeper sense. So let's try and explain what we just did. Right, what we get is that the ball went from A, it was thrown upwards, its velocity has to decrease until it reaches maximum height. At maximum height, what is the velocity? It is 0. So we reach maximum height over here because the velocity is 0. Then we change direction. So when you change direction, you go downwards. What did we choose down as? Negative. So we have to go to the negative axis. So we go to the negative axis, and it takes the same amount of time it takes for ball A to reach B. Right? So we mean that from here to here and here to here is the same thing. So that's just simple like that. Then we go to the other one, which is the simplest of all in the history of simples, whatever. Now, here you see that this is the gravitational constant squared. Right? Then here you'll have maybe delta T. Right? Now, what you must look at is that here we're speaking about acceleration. And I said to you, here in VPM, we only speak about acceleration due to gravity. And that is a constant as 9.8 meters per second squared downwards. Oh, I said this a lot of times now. Always downwards. What did we choose downwards at? As negative. So we have to plot as our negative part. We say negative 9.8 because it is negative. If it was down is positive, you're going to plot it in the positive part, right? Because we know if the graph continues like this, then we're going to have the negative part of the x-axis, and then you're going to have the negative part of the x-axis, the positive part of the x-axis, the positive part of the y-axis, the negative part of the y-axis. If you get me, those who are doing functions right now know what I'm talking about. But we are not trying to make this very deep than what it is. It is deep, but you really don't want to make it too deep. Now, this one is very simple, guys. It's always a horizontal line. So we can see that always a horizontal line. So now, because we chose down is positive, down is negative because our up is positive. We did choose up as positive here, if you remember. Up as positive. So it means that our acceleration is going downwards. So it is going in the opposite direction that we chose. So it has to be negative. So we're just going to draw a straight line like this. And that's just that. There's nothing more, there's nothing less. You'll see when we do it for the other graphs, it will still remain the same depending on which direction we chose as upwards. So if you did choose down as up, down as positive, of course, it will be the acceleration will be acting in the same direction as the direction that is chosen as positive. So you're going to plot it over here and put a straight line over there. So it works the same way, guys. You have to get the same answers despite of the direction that you choose, right? Now, of course, this is scenario number 1. We're going to be doing past papers after every scenario, and then we're going to relate every scenario that we do. Sometimes, a lot of times, it's not going to be the scenarios, but the scenarios help build up for me to have a ground to play on and explain each and every bit that I can. Because in the next video, there's some parts where I won't go deep, just like this part of acceleration being the gradient and the area being the displacement, the area of a triangle being a displacement, right? So thank you guys for watching this one. It was an interesting video. I won't lie, this was a good one. So I think I'm doing justice to VPM. So I'll see you on the next scenario.